Okay, so I think I'll go to the beginning of the um, notes on general relativity. We can think of this um, as basically we're talking about tensors, and it's strange. What is well? I tried to write on that. In any event, let's just review some of these basic concepts. I don't know if I need my mug on there. First of all, general coordinate transformations. The idea is that you have a smooth transformation from one set of coordinates to another, and it should be one-to-one and smooth in both directions. Now, it turns out that it's not always possible to do that for all coordinates in one general coordinate transformation. So sometimes for a certain part of the universe, you have one general coordinate transformation, and then for another part, you have another general coordinate transformation. But let's leave that aside for the moment. Now, tensors are quantities that change simply under general coordinate transformation. Of course, the simplest way to change simply is not to change at all, and these things are called scalars. If the scalar depends upon x, it's called a scalar field, and in fact, any physical quantity that depends upon space-time is called a field. The next simplest kind of tensor is a vector, and vectors are also called tensors of rank 1, and these, of course, are things that transform almost as simply as scalars, which don't transform at all. And in fact, a covariant vector can be defined as something that transforms like the gradient of a scalar. And if you do a general coordinate transformation, well, your tensor, your gradient of a scalar in the new coordinates is the derivative with respect to the new x prime I of the scalar in the new coordinates. But of course, the scalar in the new coordinates is the scalar field in the old coordinates. Now you use the chain rule to write the derivative with respect to x prime I in terms of the derivative with respect to xk, like this. And so then we relabel this as VK. So this is just saying that this is deriving the transformation properties of a general covariant vector by saying that it transforms exactly the way a derivative of a scalar transforms. And any quantity that transforms in this way then is called a covariant vector. And a contravariant vector is something that transforms like a coordinate differential. And this is also something very simple. According to the chain rule, if you have the change in a coordinate, a new coordinate x prime I, then that dx prime I is the partial of x prime I with respect to xk times dxk. And it's just the chain rule again. So any quantity that transforms under a general coordinate transformation like this is called a contravariant vector. And so then we've got then the three basic tensors are the scalar that doesn't transform at all, the covariant vector that transforms like a derivative, and the contravariant vector that transforms like a differential of a coordinate. I've been using Einstein's summation convention here, and the reason is that I think it makes the equations easier to understand because there's less ink on the page, or there are fewer distractions on the page. You see, if you have, instead of sum sub k equals 0 to 3 here, I think that's distracting, and it's easier to just look at this. In fact, it's yet easier to write this as v prime I. Let me see if I can use this iPad to write here. Good gracious, I'm clicking on this thing and nothing is happening. And I wonder, is it that the pencil... Okay, hold on, it says tap to connect. Well, I want to write on the screen and I'm just not able to. I do not understand. So I'm going to just charge the pencil for a while. So one thing to look at, to notice here, is that if you have a primed index that's downstairs, it stays downstairs. So in other words, look at this expression here. What you've got here is v prime sub I. So the I is primed and it's downstairs, so it stays downstairs. Here, the I is a primed index, it's upstairs, it stays upstairs. So the point is that all these tensors transform as derivatives of the new coordinates with respect to the old, or the old coordinates with respect to the new. But when you have to write down one of these rules, you might have trouble remembering, well, which is it? Is it partial x prime I with respect to xk, or is it partial xk with respect to x prime I? And the way to get that right is to make sure that your primed variables stay where they started. If they're lower indexes or downstairs indexes, then they stay downstairs. If they're upper indices, then they stay up. So that's the trick for remembering what these formulas are. Scalars of higher rank just transform like products of tensors and products of vectors and scalars. So for example, if you had 3 vectors like this, it would transform this way: A prime I, B prime J, C prime K. We've got 2 downstairs primed indices, so they stay downstairs. We have 1 primed upstairs index, it stays upstairs, and then we multiply like this, and we sum over L, M, and N from 0 to 3. And that's how any tensor of rank 3 with 2 lower and 1 upper index transforms. And one example of a tensor with 1 upper and 1 lower index is the Kronecker delta. And if we say, how does it transform? Well, it would have a primed upper and a primed lower. So it would be partial x prime I, partial x k, partial x k, partial x prime L. But that's just this, which is that. And so that's the Kronecker delta, the Heaviside. Well, I guess it isn't the Heaviside function. It's just the Kronecker delta. 1 if I is equal to L, 0 otherwise. So as I said, this Kronecker delta is a mixed second-rank tensor, and it's invariant. If you look at what it is in a different coordinate system, then it's delta prime IL is partial x prime I, partial xk, partial xj, partial x prime L. See, the two primed variables. One is indices. One is upstairs, one is downstairs. So they go upstairs, they stay upstairs or downstairs. And then the other things are partial xk, partial xj times the tensor in the old coordinate system. So that gives us partial x prime I, partial x prime L. And that's that evidently is the Kronecker delta, delta IL. So the Kronecker delta is an invariant rank 2 tensor with one upper and one lower index. So it's covariant. It's a rank 2 tensor with one covariant, one contravariant index. Now, the marvelous thing about tensor equations that Einstein realized, appreciated, and taught us is that they don't change when we change coordinates. They're the same in all coordinate systems. So a theory written in terms of tensors has equations that are true in all coordinate systems if they're true in any coordinate system. And an example is Einstein's equations of general relativity. They relate a second-rank covariant tensor called the Ricci tensor, the metric tensor of spacetime, GIK, the Riemann scalar, R, to 8 pi Newton's constant over the 4th power of the speed of light, times TIK, and that's the energy momentum tensor of the ordinary matter fields that we know about. And people have often remarked that this is an equation in which you have gravity and only gravity on one side, and you have matter and only matter on the other side. This big G is essentially 1 over a huge mass squared. The mass is the Planck mass. And written in this way, you see, this is a lower dimensional object. Normally, if you had something that was RIK, it would be of dimension 4, but this is only a dimension 2 because the metric itself is dimensionless. And R are derivatives of the metric. And you have two derivatives here of the metric. So you have something that's only transforms like two derivatives, or something that transforms like two derivatives transforms like mass squared. Whereas the energy momentum tensor of matter goes as mass to the 4th. And to make the masses or the units balance, we have a Newton's constant, which is 1 over the Planck mass squared. And the Planck mass, as I said, is huge, and that's why gravity is so weak. You see, the gravitational fields are related to the matter fields by this 1 over a huge square, the square of a huge mass, Planck mass. But the real point that I was trying to get to here was not that. It was, in fact, that we may illustrate the utility of tensor equations by looking at Einstein's equation here. And if we write this in the new coordinates, what would they be? Well, you just have primes everywhere. Or equivalently, how would this be in the new coordinates? Well, these are all second-rank tensors, rank 2 covariant tensors. So the way in which they transform is you'd have these primed indices downstairs, so they would be over here, and you'd have partial of I, xi, partial xk, respect x prime L, x prime M, multiplying the old Einstein, the Einstein equations in one coordinate system, and in the new system, they just look like this. But that's the same, these are the same, this is the same as that, it just has primes, and it's so the primes then become of no significance, in fact. So that's why tensor equations are good things to use if you can use them. Now, one of the important things that, once again, Einstein emphasized, and subsequent to Einstein, in the decades that followed, slowly we all started to realize that, well, invariants are important. And one of them was the invariant of special relativity. And it's the dot product of two 4 vectors in special relativity is the same in all Lorentz frames. Well, the generalization of that is that in general relativity, we have a much more invariant scalar. The squared separation, of the squared distance in the sense of space squared minus time squared, of two nearby points is invariant, and that invariant is given by a quadratic form in our coordinate differentials times the metric tensor. And let me tell you how I think about this. The way I think about this is that our description in terms of coordinates, of course, can change if we change our coordinates, but we're describing a physical reality that is independent of our coordinates. And that reality is made up of points of our space-time. Our space-time is curved. And now, how do we visualize something that's curved? Well, we visualize a sphere as something that's a curved two-dimensional space embedded in three-dimensional space. And I think, therefore, that we certainly can, and I think it's easy and natural to view our physical universe, which is a curved space-time, as being a space-time that's curved in a space-time of higher dimensions. And we can, in fact, always imagine that to be a higher dimensional space-time that is either Euclidean or pseudo-Euclidean. In fact, let's say pseudo-Euclidean. Pseudo-Euclidean means that there are some minus signs. In other words, there are some... Is there a problem that you can't see something? I think you can see everything. I hope you can see everything. Can you guys, let's open this chat thing here. Can you guys see the screen that I'm talking about? The screen where my mouse is, okay, good. Thank you. Okay, so let me get back then to what I was talking about. So the idea is then that we can, and mathematicians have worked this out, you can always envision our physical space-time as being a curved space-time embedded in a space that's simply Euclidean, but with some time dimensions and some space dimensions. So in other words, in special relativity, we have a metric -1, +1, +1, +1 in special relativity. In the metric of the higher dimensional space-time might have 1 or 2 or even 3 minus signs, and it has at least 3 plus signs for the 3 space dimensions we know about. It might have 4 space dimensions. I'm mean, it has three at least. It may have more space dimensions. Let me see. I just got a chat message from the grader saying that I did not send an announcement today. No. Oh goodness, where did I send it? Oh damn it, I somehow sent it to the wrong class. Oh God. All right, let me resend it. Oh my gosh, I thought I typed 466.22. Let me do it again. All right, let me find the link. Okay, now I've sent it to the right class. I've done that before. This computer thinks it's so smart that when I type something, it completes it for me, and sometimes it completes it incorrectly, which is really pretty annoying. I think in general, the completions should be in a different color initially, and then go to the standard color later. It's really annoying to, I mean, this has happened to me many times, not many times sending out class messages, but many times. Anyway, so as I said, one can imagine the four-dimensional, our universe as a four-dimensional surface, curved surface in a higher flat space-time in which the dimensions are all perpendicular to each other, and you have at least three spatial dimensions and then at least one time dimension, but possibly several time dimensions, possibly several space dimensions. And in fact, the standard cosmologies of Robinson and Walker, there are three standard cosmologies. One of them has space-time perfectly flat, and there's just the space-time of special relativity. But the other two are an open space-time in which our universe is embedded in a five-dimensional space-time with two time dimensions and three space dimensions. The other case is a closed universe in which our space-time is embedded in a higher space-time of one time and four space derivatives. And anyway, so I imagine that the points, the physical points of our space-time are scalars because these are physical. On the other hand, as if we differentiate these with respect to our coordinates, then we change the points in space-time. We make a small change in our coordinates. The point that we're describing, P of x, changes by a little bit, and the little bit is e sub I dx sub I. Since the points are scalars, the change in the points is a scalar. And these EI then are covariant basis vectors, and they're tangent to the curved surface. Obviously, from this expression, we have the points P are points on a curved surface, and as we change our coordinates, the points change a little bit, but they always stay on the surface. So these basis vectors are tangent vectors. And then the dot products of two tangent vectors, well, because they're vectors in a space that's Euclidean or semi-Euclidean. Semi-Euclidean just means it has time dimensions as well as space dimensions, but we think of them all as perpendicular. And so the dot product or the squared separation, which is dp dot dp in this higher dimensional space, is the dot product of two tangent vectors times dxi dxk. And this dot product is what we call the metric of spacetime, the metric tensor, GIK. Many discussions of general relativity skip all this business of embedding, and these can be regarded as pure descriptions, but I think they're less physical and less true, actually. Anyway, so in other words, it's natural to think of a sphere is embedded in a flat three-dimensional space. In that case, this internal metric, the zeta, is just the unit matrix, the identity matrix, which has a diagonal 1, 1, 1 and zeros elsewhere. That's a notation that's been very common for decades now. Diag, parenthesis, and then whatever. For example, for the Robinson-Walker cosmologies, the one that is closed has 4 space dimensions 1 time. So whereas the metric of special relativity is -1, 1, 1, 1, the metric of the space time, the semi-Euclidean space time in which our closed universe, if it is a closed Robinson-Walker universe, is embedded, has a metric -1, then 1, 1, 1, 1, 4 space dimensions. The open one has 2 time dimensions, which is really, really weird. -1, -1, 1, 1, 1. And that is, I think, of course, very, very amusing. By the way, what's true of these 3 Robinson-Walker metrics is that they are maximally symmetric. What that means is described in a later section of the book, but I'll just mention it now. So the idea here is that I'm thinking of our space-time as embedded in a higher dimensional space-time. It's semi-Euclidean, and the metric then is has some minus signs and some plus signs, at least 1 minus sign, at least 3 plus signs. Here I've been writing these derivatives in the standard way as using these curly D's. There's a more efficient and more succinct way to label derivatives or to write derivatives, and it's this thing called a comma notation. As I said, Dirac used it in his book, which, let me in fact show you Dirac's book. Most books on general relativity are much thicker than this. Dirac used language very well, and he was able to express everything in this small book. So he used this comma notation. It's also used by many other. It wasn't invented by Dirac. It was invented decades ago, probably 70 years ago, 80 years ago. Anyway, S comma I is the ith derivative of S, and that's partial S partial xi. So this is a more efficient notation, and the utility of an efficient notation is that it does, when you look at equations, your eyes are not distracted. Your brain is not distracted by all these curly S's and curly S's and the horizontal line and so forth. And for example, S sub comma ik is the second derivative of S with respect to xk and xi. If you have tensors, well, you have tik comma jl, tfik comma jl, looks like this. Okay. Semicolons we're going to use later to denote covariant derivatives. And if we now look at this, the fundamental invariant of general relativity, well, it's the dot product of two tangent vectors times or the dot product of two vectors that are tangent and of small length. So it's partial p with respect to xi dxi, the kth derivative of the point dxk, dotted into each other using the metric of the embedding space. And so that's ei dot ek dxi dxk, and that then is the metric tensor g ik dxi dxk. Now, you don't need to think about it. You're not obliged to envision our universe as being embedded. And if you don't like to doing that, you can just say, well, the fundamental scalar is gik dxi dxk. Equivalently, you can just say, well, this is a covariant second-rank tensor. It has, and when you multiply it by a contravariant second-rank tensor, you get something that's invariant under changes of coordinates. And you can just think of it that way if you want. Derivatives with respect to prime coordinates are written as comma x prime. So comma x prime, sub comma x prime means of xk, for example, is partial xk, partial x prime I. The inverse of the metric tensor. Well, the metric tensor is a non-singular matrix. I'm not proving that it's non-singular, but it's just intrinsically non-singular. It had better be non-singular because it gives us all these separations and so forth. In other words, if it were singular, then there'd be some dxi's such that you could take dxi, dxk, you'd make a change in the coordinates and there wouldn't be any separation in the points, and that would be just nuts. And so we insist that gik is non-singular. So it has an inverse, and we write the inverse as g upper ik. And so the inverse satisfies this rule. G inverse G is the identity. So you have G upper ik, G lower kl, summed over k from 0 to 3 is delta il. This is the Kronecker delta. And of course, this is a tensor equation, so it looks the same in all coordinates systems. And the inverse metric then is a second rank contravariant tensor, because the metric is a rank 2 covariant tensor. And this, of course, is a scalar. Is not a scalar, but it's an invariant tensor. And one can show this. This is actually an example of the quotient theory. You remember that. So let me find the quotient theorem here again and remind you of it. So I'm going to pull that to this screen and pull this back. So you remember the quotient theorem. So the idea there was, suppose B has unknown transformation properties, but its product, BA, with all tensors of a given rank and kind is a tensor. Then B has to be a tensor. And the example is B lower I, A upper I. Suppose that's a scalar for all contravariant vectors AI. And I think I went through the derivation here that you then can show that B lower k is, or B lower j is a covariant vector. So because Bj, Aj is invariant, and because whenever Aj is contravariant, it follows that Bj has to be covariant. Well, the same thing is true here. Because this G upper Ik times G lower KL behaves like a covariant second rank tensor, giving us just the identity, it follows that G upper IK is a second rank contravariant tensor. So that's basically the idea. If you want, and if we have time, I'll go through the proof of this. It's kind of a long thing, but I have it written down, and I'd be happy to go through it if we have plenty of time today. We've certainly got a lot of time left, and now this inverse of the metric tensor is used to raise and lower indices. So, for example, the contravariant vector, or to put it differently, suppose we have a covariant vector AK. We multiply it by a contravariant tensor, and namely the inverse of the metric tensor. Well, we're going to have something that's a contravariant vector. And so AI is automatically contravariant. But then we can say, well, the convention then is that it's not just any contravariant, but it is the contravariant form of the covariant vector AK. Similarly, if you have a contravariant vector AI and you multiply it by the covariant metric tensor, which is covariant of rank 2, then you're going to get something that's covariant. But it's not just any covariant vector, it is the covariant vector that's associated with the contravariant vector A upper I. So this is called lowering an index. Multiplying it by the inverse metric tensor is called raising an index. And these conventions of raising and lowering indexes apply just generally throughout general relativity. So, for example, if you have a rank 3 covariant tensor TJMN and you multiply it by G upper IJ, G upper KM, G upper LN, you get something that is a rank 3 contravariant tensor. And in fact, it is the rank 3 contravariant tensor associated with the rank 3 covariant tensor TJM. So TJMN, sorry. And so that's the story with raising and lowering. We use the metric tensor to raise and lower indices or indexes. And when we do so, we retain the name of the original tensor. Now we have these tangent vectors, EK, and we can multiply a tangent vector by the inverse of the metric, and we're going to get a contravariant vector. These things are called cotangent vectors or dual vectors, E upper I. And they are orthonormal to the tangent vectors. And the reason is that E upper I is G upper IK, EKL. And here we have this dot product in the metric of the flat metric of the embedding space. And that dot product of two tangent vectors is the metric tensor. And then the sum over K gives you the Kronecker delta. So that tells you then if I is different from L, you're going to get 0. So that's the orthonormality relation that I had in mind. The dual vectors, as I said, are called cotangent vectors or tangent vectors. Tangent covectors. Sorry, they're not called tangent vectors. They're called tangent covectors or cotangent vectors. Anyway, there's got to be a co in there somewhere. The tangent vector, the ordinary tangent vector is, of course, you can lower the index on a cotangent vector and you get a tangent vector. And that's because GKI upper I, E upper I is GKI G upper IL, because that's how you raise this index on this L index, you raise to an I index by multiplying by the inverse of the metric tensor. And then this sum over I, well, this is the inverse of that matrix. And so this is just the identity matrix. And so we get to the tangent vector EK. It's also true then that the dot product of two cotangent vectors is, well, what is it? Well, this cotangent vector is G upper IK tangent, the kth tangent vector. We're dotting that into EL, and we've just seen that these guys are orthonormal, and so this is delta LK, and that gives us then GIL. So in other words, the inverse of the metric tensor is the dot product of two cotangent vectors. Okay, well, that is all of the stuff that I actually wrote up in a detailed way. Let me see if I can write in a way that's visible on this screen now. I can't seem to do that. No matter what I do with the pen, nothing happens. I can start notes again. It doesn't matter. Well, all right. So I'm going to just forget about that. That iPad. I am just a little annoyed at Apple when the software doesn't work. And the deal is they want everything to be so. The iPhone is where they make all their money, or most of their money, and so they want everything to work the same as the iPhone. And that means they screw up the iPad, they screw up the iMac, and so forth. And now your iPhone is more valuable and more expensive, and so forth. So let me just talk about some other things then. I think instead of following the book in a straight way, I think I'm going to shoot forward here to this basic idea of covariant derivatives. And so let me just do that. So suppose we want to make the covariant derivative of a contravariant vector. Remember, I said to you that the derivative of a scalar is a covariant vector. But then I said a few minutes later that the derivative of a tensor is not a tensor. Whereas the derivative of a scalar is a covariant vector, which is a tensor. And so so the way around that, the way to solve that problem is to say, well, let's take the contravariant vector and multiply it by the tangent vectors, because then we get a scalar, and we know that the derivative of a scalar is a covariant vector. So this is a covariant vector. And when we differentiate it, we have the derivative of the contravariant vector with respect to the coordinates times the tangent vector plus the VI times the derivative of the tangent vector with respect to XL. And now, how do we get back to something that we don't want something that's in this embedding space, which is where these tangent vectors point. So what we do is we take the dot product of the kth cotangent vector with this thing, which is the covariant derivative of the scalar v. So we have ek dot, and we're taking the derivative of this scalar with respect to xl. So that's vi comma l. That's this thing here. So I've just taken all of this and stuck it there. And I switched to comma notation, so it looks like this. Now the dot product of ek with el, we've just seen that's a Kronecker delta. They're orthonormal. This is the cotangent vector is orthogonal to the tangent vector. But on the other hand, ek dot ei comma l, that's something else. So we have this expression. So summing over I, we just get that this is the partial derivative of the kth component of the cotangent vector with respect to xl, plus this funny dot product of the kth cotangent vector with the lth derivative of the ith tangent vector times vi summed over I. And this thing here turns out to be what is called the affine connection. And it's written in this unfortunate way with a capital Greek gamma, which, as I said, is kind of unfortunate notation. But anyway, this is the standard notation, and it's called the affine connection. I'm using the notation of Misner, Thorne, and Wheeler. Other people, you call this gamma Li instead of gamma IL, but it doesn't matter because in standard general relativity, in standard general relativity, gamma KIL is the same thing as gamma KLI. We'll see that later. In fact, we'll see that presently in just a few minutes. So this is the way you take the covariant derivative of a contravariant vector. And this is what's, remember I said the covariant derivative will use semicolon notation. So VK semicolon L is this structure here. And it's the lth derivative of the kth component of the contravariant vector, plus this dot product of the kth cotangent vector with the lth derivative of the ith tangent vector times the ith component of the contravariant vector v. And this dot product is written as this gamma, and I forget. I am terrible with names, and so I forget what this is. What this is called. The standard name for it is the the Christoffel symbol. That's right. And well, one of the unfortunate things about Christoffel is that his name has so many letters and it's so odd to spell. So this is the Christoffel symbol. And the Christoffel symbol then, which is also called the affine connection, is gamma K sub IL, and it's this thing here. Suppose we want to, suppose we just look at the derivatives of cotangent vectors, and in other words, we take the covariant derivative of we just learned how to take the covariant derivative of a contravariant vector. Well, one contravariant vector is the cotangent vector. So we take the lth covariant derivative of the kth contravariant, or the kth cotangent vector, and using the formula we just worked out, it's ek comma l plus ek dot ei comma l ei, and well, this thing here, you see, So in order to go to this step, I just skipped this line. So let's just look at this. The Kronecker delta, the Lth derivative of Kronecker delta obviously is 0. The Kronecker delta is the dot product of the cotangent vector with the tangent vector. And so that is the Lth derivative of the cotangent vector dotted into the tangent vector plus the cotangent vector dotted into the Lth derivative of the tangent vector. So this is minus that. So when we have this thing here, we can substitute for this is that, and we can substitute for it minus this, which is here. And now, if we just look at that, what is that? Well, this thing here is, I'm a little puzzled at my notation here. Okay, so we want to have EI dotted into this. I must say I've a little bit lost track of what anyway, we get 0, but I'm a little puzzled as to what this notation means. I just skipped over it, despite the fact that I wrote it after all. This is saying, so let's see, what do we have here? We have EK dotted into that times EI and so this is a dot product and this is a number. Well, I'm sorry. I'm just a little confused here as to what I was thinking of. So let me just skip this for a moment. Anyway, it's true that the covariant derivative of the cotangent vector does vanish. And one can show that the covariant derivative of contravariant vector transforms is a rank 2 mixed tensor. And another way of thinking of all this is to think of it in the way that one thinks of it in terms of in Yang-Mills theory or gauge theory, and what is true is that in Yang-Mills theory, the idea of the covariant derivative is that the covariant derivative of a contravariant vector would then transform as this second rank tensor. That's basically the idea, and that then tells you that the Christoffel symbol has to transform in a particular way. So let me focus on this for the moment. How does the Christoffel symbol transform? Well, you'd see it has 3 indexes. And so you might say, well, it's a rank 3 tensor. No, it's not a tensor. It is not a tensor. And the reason it's not a tensor is that although the 3 indexes or indices transform as they should, there's an extra piece. So under a general coordinate transformation, the Christoffel symbol changes as it should, as it would if it were a rank 3 tensor, but with an extra term. And the extra term actually has this particular form, which one can derive in various ways. And one way of looking at it is that x prime, gamma prime is the way it should go, plus these extra terms here. What about covariant derivatives of covariant vectors? Well, if you have a covariant vector, you can dot it, you can multiply it by a contravariant basis vector or cotangent vector or contravariant tangent vector, which is a contravariant vector or cotangent vector. Anyway, this thing is a scalar. Its nth derivative then is a covariant vector. And so this is what we want. And if we differentiate it, then we get these two terms, the nth derivative of the kth component plus the kth component times the nth derivative of the kth cotangent vector. But now we need to get rid of these cotangent vectors. And so what we do is we take the dot product with, since they're cotangent vectors, we dot them into a tangent vector, EI, like this. And remember that EI is orthogonal to EK, so we get a delta here. EI is then gives us this EI dot EK comma L, which what is that? Well, remember that this is minus EI, the nth derivative of EI dotted into EK, which is minus the Christoffel symbol. So that's how you get the covariant derivative of a covariant vector. It's the ordinary derivative minus a Christoffel symbol. And what is the Christoffel symbol? How does the Christoffel symbol go? Well, if you rewrite this as the nth derivative, if you write the nth derivative of the ith covariant derivative of the ith component of the covariant vector V, then you have VIL, and then you have minus this. Notice the IL. So you go to the Christoffel symbol IL, and then you have one index free that you have to sum over K, and you use that as the upper index of the Christoffel symbol and the lower index of the covariant vector. And then there's a minus sign because what happened here was you had an EI dot EK comma L, and that's the thing that we saw back here, way back here. Since the derivative, the nth derivative of the Kronecker delta is 0, and the Kronecker delta is a dot product of a cotangent vector with a tangent vector, you have that the derivatives of the tangent vector and of the cotangent vector dotted into the cotangent vector and the tangent vector respectively add up to 0. And so what you've got is that this is minus that. And that's what we just used. Let me try to get to the, now I don't even remember where I was. So let me see if I can make this a little, or move it over a bit. Right, that's where I was. So that's how we wait a minute, let me just, okay. So that's how we got this to work. So covariant derivatives of covariant vectors, we used the fact that this is equal to that with a minus sign, and that's why we have a minus sign here. Notice the dot product is symmetric, so this is the way we were writing the Christoffel symbol was the covariant, the cotangent, the kth cotangent vector dotted into the nth derivative of the ith tangent vector. That was our gamma. and we normally had it the EK on the left-hand side. But of course, these are dot products, and dot products are symmetric. And remember, this embedding space is just flat, and it's either Euclidean or semi-Euclidean. That is to say, it has a few time dimensions, a few space dimensions, but they're all orthogonal to each other. And so the metric there is just diagonal with plus or minus 1 on the diagonal. It's like the metric of special relativity, but with more components. So if you take covariant derivatives of tensors, what you do is you just, it turns out you can just do, you just take this covariant derivative of, suppose you were taking the covariant derivative of two vectors. Well, you take the covariant derivative of the first vector times bk plus the first vector times the covariant derivative of the second vector, and you get all these terms here. And so that's what the covariant derivative of a second rank tensor transforms as. So in other words, you get the ordinary derivative, and then you get two Christoffel symbols. And these Christoffel symbols, this is where the original tensor, which is a second rank contravariant tensor, because it's contravariant, we get two plus signs, and because it's second rank, we get two Christoffel symbols, and the sum goes like this. And in any event, the point is that a second rank contravariant tensor transforms as the product of two. We know that a second rank contravariant tensor transforms as the product of two contravariant vectors, and so its covariant derivative should transform the same way. And so it looks like this. If we have a mixed tensor, the covariant derivative of a mixed tensor is the same thing that we get from doing the covariant derivative of a contravariant vector times a covariant vector. And that then would give us two Christoffel symbols, but one with a minus sign because one of the vectors is covariant. And so the covariant derivative of this mixed tensor then is a structure like this: two Christoffel symbols, one minus sign. And on the other hand, if we have a covariant derivative of a covariant rank 2 tensor, we get two minus signs and two Christoffel symbols. And that's because the second rank covariant tensor transforms as the product of two covariant vectors. So this was another way of looking at things. I don't know whether that makes things better or not. One important thing here is that the covariant derivative of the metric vanishes. And the reason is that it is the covariant derivative of one covariant. It's the covariant derivative of a of a tangent vector, and dotted into a tangent vector, and then the first tangent vector dotted into the covariant derivative of the second tangent vector. But the covariant derivatives of the tangent vectors vanish, and that's something I skipped, and I'll go over that Wednesday and do some other things on Wednesday, which say tomorrow. So the important thing to just remember is that the covariant derivative of the metric tensor vanishes, and that is because the covariant derivatives of the tangent vectors vanish. Covariant curls. Remember, well, let's see. I guess I went so fast today that I skipped over this, but I did mention that the Christoffel symbol is symmetric in the lower indices. It's automatically symmetric the way I defined it and derived it, because I said it was basically EK dotted into the Lth derivative of EI, but EI is the ith derivative of the point. So this Christoffel symbol is really the kth cotangent vector dotted into the second derivative of the physical point, which is a scalar, with respect to the ith and the lth coordinates. But derivatives are symmetric. In other words, the lth derivative of the ith derivative is the same thing as the ith derivative of the lth derivative. And so gamma KIL is intrinsically symmetric the way I've defined things. And in standard general relativity, it's intrinsically symmetric. Now, some people have invented non-standard general relativity. And in non-standard general relativity, this can be asymmetric. This is the Christoffel symbols are not necessarily symmetric then. Anyway, suppose now we take the covariant derivative of something that is, we build in some anti-symmetry. We take the ith covariant derivative of the lth component of a covariant vector, and we subtract the lth covariant derivative of the ith component. Well, we're going to have this thing here, and we have that thing there. But notice we have minus VK gamma K Li plus VK gamma K IL. These two guys cancel because gamma Li is the same thing as gamma IL. So that's the same thing as the ith ordinary derivative of the lth component of V minus the lth derivative of the ith component of the covariant vector V. So that means then that this structure transforms as a second rank covariant tensor, even though when you first look at it, you'd say, oh, it's not a tensor at all because it doesn't have any covariant derivatives in it. Well, because of anti-symmetry, you don't need the covariant derivatives. When you put them in, they disappear. And that is why in electrodynamics, the key quantity, the electric field, the magnetic field, they are anti-symmetric derivatives of a 4-vector, a covariant vector called A sub L, or A sub I. And so, in other words, it's the ith derivative of A sub L minus, I'm sorry, the ith derivative of A sub L minus the lth derivative of A sub I is the Faraday field strength tensor FIL. And so it's the 4-dimensional curl of a covariant vector field, and that's generally covariant, a generally covariant second rank tensor. So in other words, this thing of electrodynamics, in other words, Maxwell 150 years ago or so, and Faraday invented, or let us say, put the finishing touches on electrodynamics, classical electrodynamics. And in doing so, they presented us with equations that some of which are generally covariant, and tensors that are generally covariant, even though the notion of general covariance wouldn't be discovered for another 50 or 60 years in the early 1900s. 1915 or so. And whereas the Maxwell and Faraday, their theory was basically formulated around 1860, 1865, somewhere in there. Anti-symmetry is really useful, and it's, in fact, I don't think we appreciate how significant anti-symmetry is. I know I don't, and I don't think, I mean, maybe Ed Witten does, but apart from Edward Witten, I don't know if anybody else understands fully what the implications are of anti-symmetry. The reason I say that is that, you know, we have these fermions that are that obey anti-commutation relations, and now why is it that they obey anti-commutation relations? Well, we don't really know, and but somehow they do, and I think it's a little bit like the situation with Faraday and Maxwell back at the time of the Civil War. They formulated electrodynamics, classical electrodynamics, in terms of quantities, some of which were generally covariant under general coordinate transformations. And now what we've got is a use of anti-symmetry in physics, and I bet that it will eventually find that we've accidentally, or not accidentally, but we've come upon structures, anti-symmetric structures that we know are there, just as Maxwell and Faraday knew that the field that E and B were anti-symmetric derivatives of the spore vector A. So too we know that there are the fermions as well as bosons, and the anti-commutation relations as well as commutation relations, but they didn't appreciate the word general coordinate transformations, and we don't appreciate something else, which is why we have fermions and bosons. Anyway, suppose we take the covariant derivative of a second-rank tensor. Well, it is of this form. We've just worked through that. Namely, we have two Christoffel symbols, two minus signs, because it's covariant. Now, suppose that this tensor is anti-symmetric. In other words, AIL is minus ALI. So let's add together these three covariant derivatives. And let's suppose that A is anti-symmetric. So then if we do that, just baldly, we get this one is line 1, this one is line 2, this one is line 3. And then we see all the Christoffel symbols cancel. So let me do one for you. AMK. It's right. Yes, okay. So it's these two, for example. You see, IL and LI are the same, but MK is minus KM. So these two terms cancel. The same thing, these two guys cancel. IM is minus MI, but KL is the same thing as LK here. So those two cancel. And then finally, this one cancels that one. Again, the Christoffel symbol doesn't care about the order of its lower indexes. And on the other hand, we've said that the A is anti-symmetric. And in fact, this also occurred in the Maxwell and Faraday equations. As I said, the field strength tensor is anti-symmetric by construction, and the homogeneous Maxwell equations then are given by the sum of three covariant derivatives of an antisymmetric tensor F. And so these are tensor equations that are valid in all coordinate systems. And you see just automatically how it is that they cancel. Because you see, when you take fjk comma L, then that's ak comma j comma L, but also minus a j comma kl. And then you do the same thing for these two, and everything cancels. And so this is an example. The homogeneous Maxwell equations are generally covariant, and of course they're essentially well, they're kind of like 0 equals 0, well, anyway. All right, well, we're out of time now. I hope that I haven't been going through things so much faster than I should. I'm a little worried, but anyway, you know, the homework problems are not going to be super hard, so I think we'll all be okay. Tomorrow we'll have the Wednesday class, and I hope people will ask questions either by using the chat box or just by talking. Because I realize that in order to ask a question, you have to have a pretty good grasp of the subject, because you have to say, well, why is such and such the case? You have to know what such and such was and what the case was. Otherwise, you wouldn't be curious as to why the two things are related. And so that's one of the problems with asking questions. You have to know essentially what it is that you have to understand the subject pretty well, and maybe I'm going too fast. Well, I'm going to end the class since we are out of time, and tomorrow class starts at 5:30. And in general, class is always Tuesdays at 5, Thursdays at 5, Wednesdays at 5:30, and office hours are Mondays, usually 4 to 6. But this past Monday, I had to switch it to 1 to 3 because I had a medical thing occurring on 4 o'clock and had to be there at 4:30 and 3:30. All right, let me end this thing. So have a nice evening.